Hi, my name's Sandra Brantingham, the Aurora. We're also going to look at Noctilucent clouds, and we're going to look at a little phenomenon called Steve. So, second slide. This is my job. These are the adverts. Aurora Noctilucent Cloud Director and Council Member for the BAA. I've been doing that job for just over 4 years now. The next slide. I'm Aurora Noctilucent Cloud Director for the Society of Popular Astronomy, and I've been doing that job since 2003, so quite a long time. Some nice photographs in the background, you'll see. So, right. So, next slide. Aurora and NLC. Right. So, I'm just going through the bits. What's its history? That's what I'm going to cover. What's its source? What is the Earth's involvement? How do I track it, and what do I look for? What's new? What's coming up? How does it affect other planets? And then we'll have a quick look at Steve. Finally, NLC, the summer job. How to photograph stuff and camera ops. And a final plea. Remember, I've got one easy rule. There's no such thing as a stupid question in astronomy, so ask as many questions as you like, and I'll get round to all of you. Okay, next slide. Auroral history. Pre-Christian, Greek, Chinese, Japanese, Korean, Viking. It goes back thousands of years. The medievals called battles in the sky. That's not far out of what's actually happening. There's a little town on the Canadian-American border that has more visitors than it does population. It's called Niagara because Niagara Falls are there. Now, I wouldn't recommend going over in a barrel because it's extremely dangerous. And funnily enough, so's the Aurora. And yet we seem to be fascinated by what's dangerous. So, it was used to be thought it was reflections of the sun from the polar ice. That's a bit daft. Well, if you consider that in the winter, the sun doesn't shine on the polar ice at all. In fact, it's completely black dark for 6 months. So, they had all sorts of very strange ideas, but some of them not too bad. Next slide. Now, you need your imagination for this, but this is supposed to be a 30,000-year-old BC cave drawing of the Aurora. Now, like I said, you need your imagination, but it's just showing that it goes back an awful long time, unlike Noctilucent clouds, which I'll cover later. Okay, next slide. And this is where the name came from. Galileo Galilei termed the term Aurora Borealis after the Aurora goddess of the morning. Borealis means northern, and the one down south is the Aurora Australis. But he thought it was basically the sunlight reflecting from atoms flown through gas of the upper atmosphere. Again, they weren't quite sure what was going on. Next one. So, scientific auroral studies. In 1773, Captain Cook got down south, and there was the Aurora down south. That was the first time the Aurora Australis was seen. And then the big one, in 1859, on the 2nd of September, the Carrington event. There was a big flare on the sun, watched by a guy in Cambridge called Carrington. And about a day, or less than a day later, we had massive aurora, and that positively linked it to the sun. So, basically, next slide. Sun is a fire, and the aurora is its smoke. That's a simple view of it, but it's pretty accurate. So, next slide. There's the sun, and it's a cutaway drawing. Basically, 15 million in the middle. Creates all these electrons, free electrons come charging up. Take ages to get to the surface, but once they do, they blast off into the sky. And we'll see how they travel. How does matter escape? Next slide. First one, it leaks. The best one I can think of this is if you've got a pressure cooker. Do you remember the old pressure cookers? You used to heat them up, and they would sit there, but they would always leak a bit from the side. Now, this is despite a paper just before we all discovered all the bits and pieces that said the sun was too powerful and the gravity wouldn't allow it to leak, but it does leak, and it leaks roughly at about 300 kilometers a second. That's the speed the matter tends to throw off when it's not being blown off. Coronal holes. Again, this one's a good one because the sun is a rotating mass, but it's a gaseous mass rather than a solid mass. The poles spin slower than the centre, and that causes a tearing action. It's a bit like if you're doing a belly dance, moving your stomach across, back and forwards. Don't ask me to do it, I'll cause myself an injury. But basically, it causes splits. And when these splits occur, we get jet streams coming out depending on the direction they're pointing. If you see a picture and the coronal hole's right in the centre, it's pointing at the Earth, and it normally comes out no faster than 800 kilometers a second. It's normally about 500 to 600, but the fastest I've seen it is about 800 kilometers a second. Collapsing magnetic fields, and I'll show you pictures of those, so I'll explain. And then there's exploding magnetic fields. So here's your standard sun, the size of it, and bits leaking off it. Magnetic loops all over the place. Absolutely chaotic. The dark areas on the next slide are the coronal holes. And you get jets of matter coming from these dark areas. Right. We go to the next one, next slide, and that should be the sun with a big loop on it. Now, say that's a magnetic field holding it. If that collapses, and the easiest way to think of this one is, have you ever been to a bonfire and it's burning down and there's a huge piece of wood and it suddenly collapses down and sends loads of sparks? That's the same effect as this. So a collapsing magnetic field will throw out, and again, about 800 kilometers a second. Right, next slide. Now you can see a nice picture of the sun with two spots on it. Now that has a magnetic field linking those two spots. What you've got to imagine now is that instead of collapsing, it twists and twists and twists and twists. And the best way of this one is, do you remember the model aeroplanes that used to wind up and they said, do not wind beyond 80, so you'd wind them up, excuse me, and you'd fly it and your mate would wind his up and it would go a bit further, so he'd put some more turns on, so you'd put some more turns on, so he'd put some more turns on, so you put some more turns on, and then the elastic broke, the thing whipped back, cut your finger. Well, it turns out the same thing here. As it twists and twists and twists, it eventually explodes. These are the big ones. These are the ones that we call solar flares and coronal mass ejections. And these can hit well over 2,000 kilometers a second. If those spots are right in the middle, then that's like Vinnie Jones with a double-barrel shotgun pointing straight at you. And that's going to hit the Earth with all the resultant fun that can cause. Now, the English have a double-barrel shotgun that you have to reload. The Americans have a single-barrel shotgun, but you can pump action load it. The Sun has a double-barrel pump action shotgun. In other words, it can fire off blasts, and before that blast gets to us, it can fire off another blast. So if we're in the target range, and that's anywhere 30 degrees either side of the center, and it starts firing off, like it did in 2003, then we get auroras like it's going out of fashion. Okay, next slide. So the interplanetary magnetic field. I'll have to change my false teeth. First bit, particles leaving the sun make up the solar wind. This is what we call the solar wind. It's all the bits and pieces that spread out into space. The sun's magnetic signature is carried with it. And I'll show you a picture of that shortly. I used to always say it extends the edge of, but it actually defines the size of the solar system. As we learned in the talk this morning, the Voyager ones crossed the boundary between where the solar system ends and intergalactic space starts. And so not only does it control the size, but it will vary with the activity of the sun. So our solar system can shrink or increase as the pressure of the solar wind. And it affects all planets to a greater or lesser degree. It is quite effective, especially over long term. So next slide. Now you should have a picture of Comet McNaught over Keith, just about to wipe it out. Probably best thing for it. You can just see a tiny little thing above the clouds. This is what annoyed me, because what they saw down south, and this is the next slide, was this spectacular display. But why I'm showing you this is if you look at the trail, you'll see that it's broken up into lines. In other words, the comet's dust is lining up along the magnetic fields. And you can see there's an actual curve to it, because there's a copy of the sun down the bottom. So this is actually showing you what we did when we were at school. You've got a piece of paper, there's a lump of metal under it, you scatter some iron filings, tapped it, and all this pattern. Well, this is up the ante. Here's a comet throwing off magnetic particles that have been shaped by the solar wind and showing the Parker spiral. But that is an actual view of the actual solar wind. Okay, next one. So the Earth's magnetosphere you should have now. And there's the sun. And this is a rough idea of what happens. So out comes all the particles. It strikes our magnetic field. Now, believe you me, if we didn't have a magnetic field, if you looked at me now, I would look more like a cockroach. I'd need it. I'd need that armor to survive the blast of solar wind coming straight down on us. As it is, we've got a magnetic field that shields us from the worst that the solar wind can do. And what happens, at first we thought it used to just leak in at the poles. Now we know it shakes the tail, the bit to the right, and sends vibrations up the tail, which then jet into the poles. Funnily enough, the magnetic poles and the North Pole are almost aligned. Not quite, but there's no guarantee that to be the case. And we know by geology that that has changed. In other words, the north-seeking pole has been the south-seeking pole. So this isn't always the case, and it also moves. And as you'll see later, that might have an effect on other bits and pieces. Next slide. This is what I use to try and calculate what's going on. So if the solar wind's doing about 300 kilometers, and you'll see the little dot, it takes about 5.5 days. The faster it goes, up to 800 kilometers, it'll take about 2 days to get here. The bigger ones, and I've got another graph to show that, but I'll leave that out for the moment because the sun's ridiculously quiet. But it can get here in about 13 to 14 hours if it's a really, really powerful explosion. But this gives me a rough idea what's going on. So if I see a coronal hole and it's on the center, I can say, right, it's doing about 600, it'll be here in about 2.5 days. And funnily enough, just as it's moving off the center, the effects of it tend to arrive. I don't know what NASA used, but I think they used roughly a similar sort of system. We can't tell how fast the coronal holds, so it's basically a guesstimate. And we won't know until we get satellites really, really close and pass us data and say, right, now we know it. But most things are the Lagrange point, which is only 1 million miles away from us, so we're stuck with this at the moment. So, next slide. Right, this is the ACE Magensweepum. There's another one, the Disco, but I can't download that one because it's a live one permanently. But basically, it shows you what's going on. Now, you can see all sorts of bits at the side. The top one, you've got two lines, a white line and a red line. Now, the white line is the total power. It would be always above the 0 line. If you can imagine another line paralleling it but below the line, the red line cannot go either side of that. So the white line limits the red line. The red line tells you if it's positive or negative. If it's positive, the Earth tends to bounce the material off. If it's negative, then it tends to break through. And the more negative is, you'll hear us saying BZ, the more negative it is, the more chance you have of an aurora. You come down to the fourth one, then the speed, and the other thing you'll have to watch is these numbers, because they'll change the scale. You can see there it just covers from 320 to 440, but they do tend to change the scale as if it suddenly gets a blast. You can see it goes along fairly gently here, but if there's a coronal hole, it will tend to gently rise. If it's a coronal mass ejection, it's like a cliff edge. It goes vertically straight up, and this will go from 300 to 400, and then it'll suddenly change from 300 to 1500, and you'll see this will all suddenly look quite flat and a vertical line where we had the impact. Temperature in degrees Kelvin. Again, all of these things, the density, the temperature, tend to rise with the blast, but the main ones are the speed and the red line. If the red line is low, and low for a long time, good chance of aurora. Okay, the next one, and I find this the most useful. If you go into space weather, down the side, there's this little auroral forecast map. And I find this incredibly accurate, and they're trying to update it and make it more accurate by taking reports. But if you're in the green area, there's a good chance you're going to see the aurora. As you can see, Iceland is blockaded with it, bottom of Greenland, and right across northern Canada. Earlier on, it might have just caught the northern tip, so we might have seen it if we'd had good weather, of course. But it gives you a rough idea, and this one is really, really good, and it's pretty well updated, so it's only about an hour old. Next one. This is a rough idea, and I find this a bit awkward because they changed to this, but it gives you a rough idea of the actual KP indexes, and it's very blocky, but if it starts going into the yellows or into the reds, you really are looking at aurora. And from yellows upwards, these are what you call G-class storms, and you can see on the right-hand side at the bottom, G1, G2, G3, G4, and G5. And these are what I report in my little article in the BAA. So how many of these we get? The next one. Right, this picture of a couple of dresses. We all know this picture, right? And this is a real problem. I've stood next to people and looked up and said, oh, there's that colour. And they say, I can't see it. I don't see that. So what you see on the aurora can vary with your eyesight. You might just see a whitish mess. So next slide, colours. So first bit, green. This is the most predominant colour, and it's oxygen at 50 to 140 miles high. That is the primary thing you'll see. I'll come on to what you actually see and how you see it just a bit later, but these are the colours. Next one, red, oxygen at over 140 miles high. Basically, it's got more room to move, so it makes a bit more noise. Next one, yellow, pink. Once the activity gets high and there's lots of activity going on, you get a mixture with the reds and the whites and greens, and that gives you your yellow and pink. Finally, when it gets really, really active, the last one, blue-purple, it manages to kick nitrogen into action. Now, some of you must be asking, well, hold on a minute. There's only 20% oxygen and 80% nitrogen. What's going on? Basically, nitrogen... Well, I'll tell you a story. When I was doing a welding course, there was one guy who was a bit lazy, and the instructor was explaining how to cut And he said, we use an oxyacetylene cut and we're surrounded by nitrogen. And this guy said, why are you surrounded by nitrogen? And he looked at him with an eagle eye and says, because it's like you. It does nothing. In other words, it's an inert gas. It's very, very difficult to kick into life. Oxygen, on the other hand, well, anybody who's had a car will know it rusts. It oxidizes with metal. If you breathe too much of it, it's actually poisonous. And last of all, and I wish you never come across this, an oxygen fire is one of the most terrifying things. In other words, it's a very lively gas, so it's easy to kick into life. So, next slide. This is what actually happens. An energetic particle comes in, and it knocks an electron from the an inner ring to an outer ring. Right, now that gets it into an excited state, it's all full of life. However, it doesn't like being in an excited state, and it drops back to the normal thing. When it drops back, it kicks off a photon, and it's that the light you see. So questions always come to this one, why at 50 miles? Well, it's at 50 miles to 140 miles, it's like the Goldilocks zone. It's not too dense, and it's not too thin. In other words, and the electrons do get down here, the density of the atmosphere is too dense for them to cause the excitement. Above 150 miles, 250 miles, the atoms are too fast-spaced, but just between about 50 and 150 miles, the atoms are close enough to give off photons and to resonate. And just think of it like glasses of water when you fill them up. If it's full up, it doesn't make a sound. As they move it down, it makes more and more sound. By the time it gets empty, anyway. So, next one. Now, this is a picture of the Aurora from the space station, and that's the only thing that will fly through it. You think you can fly through it, you can't. It doesn't start till 50 miles up in the top of the metosphere, basically. Next slide. Right, this is a picture of the Aurora generally, but you won't see that, right? And I want to go through this picture quite closely. It shows you, on the bottom, you can see bits of orange. This was caused by the Aurora colorless and buckiness. In other words, it's pollution. The green wouldn't look green to you, it would look white. The reason for this being that the Aurora creates its own light. So if it's fairly weak, then your eyes will see it using rods. Now, your eyes are made up of rods and cones. Cones will detect color, and they're based in the center. Rods are more scattered around the cones, and you use them at night, but they'll only do black and white. So unless the Aurora gets very powerful, you won't see the green. You'll see a white blurge. So you'll take a picture of it, and whoa, it's green. Ah, it's the Aurora. Now, if you watch it for a while, your eyes will dark adapt, and you might start to pick out colors. But again, it'll depend on your age, it'll depend on your eyes. It's one of those things that I can't guarantee what you'll see, but once you get a really good storm, you can get ones powerful enough to read newspapers by, or more than likely what we normally get up here, just a weak green glow at the edges. Now, once it starts to, next slide, that's a picture of my house. Once it starts to build up, you can see what we call curtains and ripples start to form. Next slide. This was in 2003, the one I was going on about, the real big blasts. And that white dot on the left-hand side is Mars. In other words, this is looking almost south. That is southwest, basically, in the center of that slide. And you can see every type of color there. The oxygen greens, the red. This one was seen as far south as the Portuguese Algarve. I had a friend who was running the Dutch side, and he missed it completely because it was clouded over. But his friends in the meteor section had gone down to watch a meteor shower, and had seen the aurora to 40 degrees in the Portuguese Algarve, which means that one would have actually crossed the Gibb Strait, so it would have been visible in Africa. So it can spread quite a distance. This is, next shot is looking straight up. And this is what they call the corona, not the virus. This is the junction. Now, it's never directly overhead. It's slightly offset due to the variation of the magnetic pole to the pole. But it's almost like walking in the temple of the gods. And once you've seen it, it really does sort of tick the box for the bucket list. Okay, next slide. Excuse me. Now this one's a picture of proton aurora. You won't see it. It's in ultraviolet, so we can only see it by satellite. And the reason I'll show it is you'll see about Steve later on. But there you go. So, what have we been doing? These are the cluster dancers. They were called the dancers because they could move. So, salsa, samba, rumba, and tango, just to prove scientists aren't boring. And their idea was to have a look at various bits of aurora and see what they could find. And they solved this one. Now, the next slide, you should have Knock Hill with a green mass above it, and then a dark bit to the left. Now, that's what we call black aurora. There's an argument who named it first, but as far as I know, it was a group of Canadian students, and they didn't want to know what it was, so they called it black aurora. They managed to get the clusters to fly through it, and they found that what it was electrons going out thousands of miles in space. The easiest way I can describe this one is I talked to a fireman, and he said when you're in a fire up above it and you squirt a hose down, the hose tends to drag air along with it, so it cuts a hole so you can actually see right into the depth of the fire. And this is the same thing that's happening. Electrons are shooting out and cutting a hole in the aurora, so you can literally see the sky through it. So that was a good discovery, and when I started doing this, I didn't think we'd get many auroral discoveries. In fact, we've had a few. So, next slide. You should have a massive blue. That actually is Jupiter, and that's the auroral path caused by Ganymede, Europa on the planet's surface. So we get auroras on other planets. Next slide. There's Jupiter. And sorry, Saturn. My apologies. And you can see the aurora rings on either side. You'll notice they're a different colour because they're different gases. So we can actually analyse the gases by the colours. Yeah, excuse me. Right, next one. Now the hard bit. You should have the average sunspots 1610 to 2000. This is basically the plot of how many sunspots we've had, and you can see it's almost like a heartbeat, with the exception between 1650 and 1700 when there was none, and that's called the Maunder minimum. Hopefully we don't have one of those, but basically it means there was no sunspots, very little coronal holes, and very little solar activity. Thames froze and stuff like that, so it does affect us. Right, the next slide is the current solar cycle, and you can see that back in 14 and 15 it was banging away nicely and sending out lots of solar stuff, lots of aurora. But if you go to 19 and 20 along the bottom, it's right on the bottom, and we're just about to swap over another cycle. In fact, there's already been a couple of sunspots of the new cycle. Right. I'll go to the next slide, but before I do that, is there any questions so far?
None so far. Sandra. What I suggest we do is we go to the questions at the end.
Okay.
And then that will give people time to sort of type in and sort of think them. I mean, anyone's free to type in any questions as we go along as well.
Yes, that's what I'm saying. Yes, I'm just having a break as well. My throat's getting a bit dry.
Yeah, good idea. No, I'd say I think we're keeping pretty much in step with the slides. There was once or twice when I got ahead of you, but I think all going well.
That's all right. Yeah, I've got to remember to say the slide.
Yeah.
So you should have welcome to Steve.
Yeah, so that's where we are at the moment.
Right, okay. I'll go through the bits and pieces on this. Right, so when I was just joining the BAA as a director, and that was April 2016, Alan Clitheroe sent me this picture. And he says, yeah, I've got the Aurora, but what's this weird thing on the left-hand side, this beam? And he described it as very difficult to see, but the camera saw it very well. In other words, it was almost infrared. I was up to my neck in muck and bullets at the time, but I thought, oh, I'll have a dig around at that. I've never seen anything like that before. So it was seen in Canada, the UK, 2016, 2017, lots of them. Next one. It was called a proton arc. Well, I knew that was wrong because, as I showed you, protons can only be seen from space. A stable auroral red arc, a SAR arc, or an auroral comet. And it does look like a comet, I must admit. Next bit. It was named after a book character by the Alberta Aurora hunters. There's this character who looks over a fence, and anything he doesn't know, he's got to call Steve. So if he sees something he doesn't know what it is, it's Steve. And the Alberta Aurora hunters decided, in their wisdom, to call it Steve. It was investigated by Professor Eric Donovan at the University of Calgary, and he was the ideal chap to do it. Next slide, because he had access to these beasts. Right, they look like vacuum cleaners, but they're swarm satellites from the European Space Station. There's 3 of them, and he found that one of these had gone right through the beam. Brilliant. So we could find out exactly what it was. And it was a jet of gas, 25 kilometers wide, at 300 kilometers height, and it was heading west. The surrounding gas was moving at 10 meters a second. The jet was doing 6 kilometers a second and was 3,000 degrees hotter. In other words, it was like a blast of fire going down. Next one. So there's what they decided, it can't be a character, so it's going to be strong thermal emission velocity enhancement. There you go. This is my first sighting on the 18th and 19th of March. In the last journal I sent in with Steve, there was a photograph of this taken in Leeds. So it can be seen all the way down. This is almost looking west, so it's well to the left of the main Aurora display if you're looking north. And as you can see, there's the old Pleiades and the Hyades. There's Orion on the left. Added to this, what I also saw was directly over our head, and the camera didn't catch it, but there were patches, and they were moving very rapidly down, but coming down to the right of this column. So coming down more or less through the Pleiades. And then right at the end, the last patch, the column moved across and seemed to catch it, and then it disappeared. So what was going on, I don't know. But there's a lot to learn about it. So Steve is the visual part of SAID. Right, for those who haven't come across SAID, sub-auroral ion drift. Sub-auroral, right. The aurora is defined as anything between 65 and 80 degrees. So north or south. So anything below that is classed as sub-auroral. Ion, that's just free particles, mainly electrons, but basically charged particles. Drift. Now this is the bit that got me. Drift was anywhere from 4 to 12 kilometers a second. I thought, oh, that's a bit fast. But then I thought, if you're dealing with something like the solar wind, which is minimum 300 kilometers a second, then maybe that's fair enough. So, subaraural hydra. It was studied in the 1990s, and it's an east to west movement of electrons. But one thing, and I read all these papers, they never mentioned anything visual. So it seems to be a visual manifestation of what's going on in SAID. And this has managed to start to tie down what is actually going on. But there's still a lot we don't know about it. It's still under debate and discussion, and it's still being looked at. I thought, 2016, 2017. Next slide. There's Steve by Dr. Russell Cockman. And not only that, I found out that 100 years ago, and I'll just check his name, but his name was Carl Stormer. And he saw Steve, but he called it, now let me see, get this right, high altitude detached subaraural arcs. So there you go. So it has been on the go. What my question is, though, on it, and you might have different ones, but my question is, why are we starting to see it with weak auroras? My only thing I can think of is the movement of the magnetic pole, which is very rapid, causing problems. But I've no idea, really. So anybody any better ideas, I'm all ears. Right. Okay. We now come on to the final bit, Noctilucent clouds, the summer job. Okay. Next slide. So what is it? Well, I can tell you a nice story with this one as well. When I was young, if I was good, they used to take me to a park called Backhouse Park. Now, I used to think it was just called Backhouse because it was at the back of the houses. It was actually named after Thomas Backhouse. And he was an avid cloud watcher. And back when he lived, back in the 1800s, late 1800s, it was a good time for clouds because Krakatoa had erupted. And it gave spectacular sunsets, and he was in his element. But then he noticed something after they faded, which they faded after about 2 or 3 years. These electrical blue things appeared. They only appeared in the summer months of May, June, July, and they were very, very strange. Called Noctilucent, Nocti meaning night and lucent meaning shine. Next bit, form high in the atmosphere, 50 nautical miles. The place we call the mesosphere. For those of you who don't understand the atmosphere, it's split into layers by temperature. So we start at the bottom, the troposphere, where we all live, where airplanes fly, where all the mountains are. Temperature reduces. Next one up is the stratosphere. Temperature increases. Next one up, the mesosphere. That's where the temperature reduces. And if you look at coming on more common, ice crystals form on dusts. So when and where? Between 50 and 65 degrees north. But that's spreading now further south. After sunset, when the 12 degrees below the horizon. From May to early August in the north. And from November to February in the South Atlantic. So, the mesophores, right. It's high. That's the bit that we're interested in. And the temperature drops in the mesosphere. The mesospores, if you ever see the word pores, it just means edge of. So that's mesopause is the top of the mesosphere. Above that is the thermosphere, and the temperature increases. So anything rising will stop at the mesophores. It's high. It's 80 kilometers or 50 miles high. It's very cold. Minus 123 C or 150 degrees Kelvin. That's temperature above absolute zero, by the way. It is very dry. It's almost like Arctic tundra, so you leave marks in it, they're going to stay. It's very difficult to get there, stay there. Balloons can't get up to it. Rockets go through it. Well, like rockets, you know, they're there and then they're gone. So getting there, it's almost known as the unknowosphere, because people have very great difficulty studying it. So what's its source? Next slide. Well, this is a rocket trail. So there's one source. Volcanic eruptions. As Krakatoa was one of the most powerful blasts, if not the most powerful blast known in known history. It sent a vertical column, probably high enough to break through the stratosphere. Once it broke through the stratosphere, it would rise to the top of the mesosphere, and that's probably caused the start of it. They had not been seen before that. Unlike the Aurora going back thousands of years, they hadn't been seen before that. Man-made rocket trails. The worst offender was the space shuttle. But all rockets going through the mesosphere will dump dust and bits and pieces. Meteorite smoke. Yeah, bits will fall down. The meteorites can break up in the thermosphere or the mesosphere, so that's where most of them break around. So leaving debris into the mesosphere. And finally, global warming. We still don't know about this one. That's why a great deal of study has been put into it. That's why your reports are important. Okay, next bit. NLC from ISS. You can actually see it. Apparently Tim picked up some pictures, although he hasn't sent them to me yet. Yes, it can be seen from space. Next one, NLC from the AIM satellite. Excuse me. And you can see this was one of the early satellite ones. The next one, right, you've got the temperature and the moisture in the Noctilucent. And this was a temperature graph that was sent into space weather. The red one is the one you're interested in. Now, at first they said, oh, it's not going to be very different. But you can see on the right, as it goes down and down, and then it gets below everything. So in other words, it's getting very, very cold on the left-hand side. On the right-hand side, again, the red one, at first it starts in the middle, but it tends to end towards the top. It has that little glitch, but by and large, it's a lot damper. So those two characters are giving us an amazing one. And then the last one I looked at was last night, which is about 3 days old, and it had patches down to 52 north. Now if you've got clear skies, you should be able to see 10 degrees beyond that because of its height. So it should have been visible down to about 42 degrees north. But this is the data, and you can see therefore that this season is going to be a pretty good one. And I've already got over 150 reports. So, right, next slide. There's the map on the 21st, and this was when everybody and these dogs saw it. It took me ages to catch up. Now you'll see some of the problems we've got. If you look over the British Isles, it seems to come to a complete halt. Now that's obviously not the case. So it's obvious that the cloud extended further, but the satellite didn't pick it up. Because the satellite takes various pictures and then they're all slotted together, we might get some of it, but we might not get the entire picture. If you look to the right, you can see patches going down to almost 50 north. It's pretty much circular above of 75 north there. And you can see also there's a bit of a lump spins around, and it actually rotates in about 5 days. So we've got this almost offset jelly sort of going round of a Noctilucent cloud. And we try to predict when it's going to be good over ours, although we can't predict the weather very well at the moment. We're not in northeast Scotland. Right, next slide. Right, if you want to take pictures, great. But look at the back of the camera. It's complicated. As was pointed out when I was down at Cottingham, it was a brilliant thing. When it goes dark, all these buttons move. It is difficult. Added to that, I was a professional photographer for 9 years, and this thing caught me out. To get a picture, it has to do everything, otherwise it refuses to take a picture. So you go to manual. As soon as you go to manual, you have to set up exposure at the time. That's fair enough. But then it refuses to take a picture because it can't focus. So you go to manual focus. It does not go to infinity, it goes slack. So you've got to focus it and then not touch it, because if you touch it, it goes out of focus. And believe you me, the amount of out of focus pictures I've taken, let alone seen, come over my desk, is amazing. So get to know your cameras. If they're complicated beasties like mine, get to know them well. Focus and then try not to touch the lens. If you do touch the lens or alter it, refocus. A final plea. I love all your reports. You're wonderful and it's great, and I will reply to every single one of them. However, please, when you're sending reports in, write your full name, stay where you were, just the town will do, geographic if you can, use the double date, and then put the pictures on as an attachment. That means Ken and I can get our reports made in, you'll appear in the journal, everything. If you could do that for me, that would be fantastic. Thank you very much for listening. It's very weird talking to the phone, but I hope I didn't bore you too much. And now I'll take any questions.
Thank you very much, Sandra. That was a fascinating talk on Aurora, Steve, and NLC. We're already starting to get in a few questions, which is good. What I'll do is I'll look on for Zoom. If you use the Q&A buttons, which will be down the bottom in the middle on most, they might appear sort of elsewhere if it's sort of on some other sort of
I'm going to try and link
hardware.
into Zoom then and see if I can.
What I'll do is I'll read them out to you, Sandra.
Okay.
Because I think that, because I'll also look out on YouTube just in case anyone writes in anything.
Right.
So the first question is from Pete Sherman at Sigma. And he says,
Yeah.
Hi, Sandra, great talk. Do you think that the link between NLCs and air pollution is correct? Personally, I think it's a rubbish theory, but I'm interested in your views.
Any air pollution will eventually travel up by hook or by crook to NLC. The biggest polluters, as I say, are what dumps there. The biggest stopping of any air pollution moving up is the change in temperature, i.e. The stratosphere increase in temperature. So most of the rubbish, unless it's blasted up or blasted into it, will tend to stay in the troposphere. So we keep it all down here. So yes, Steve, I think that's you're probably right on that, Pete. How it gets up there, like I say, it was never seen before the late 1800s. It's one of a new phenomenon almost by any form of astronomy standards. So yes, if there are mechanisms moving stuff up, I don't know of them, but I'm not going to say they don't exist. I.e., sprites are new since we started. You get electrical storms. Maybe something can actually blast up in through there, but at the moment I don't know anything that will save volcanoes, which will actually get through the stratosphere up to the mesosphere.
We have a question from Hazel Collett, and because she's on the panelists who spoke earlier, she's not able to type it in, but I can read it out, which is why are NLC wavy?
It's basically if you imagine if it was flat, right, like the sea is flat, right, what makes the waves wavy? It's the wind. And the wind, I think it's doing about 200 to 300 knots as it whips it round the poles in 5 days. So now they tend to call this gravity waves. This is the posh name for it. It's not actually gravity waves, but it basically basically the rotation of the Earth plus effects from storms down on the ground that actually send shock waves upwards. So basically, it almost forms like a sea, if you like. It's literally, if you ever go scuba diving and look up at the surface of the sea and see it rippling about, it's almost identical to Noctilucent clouds. So we're at the bottom of a sea, and you imagine looking up. So that's the main reason all this chopping and rippling caused by A, the rotation of the Earth, and B, the storms beneath it.
Next, we have a question from Keith Pearson. He says, excellent presentation. What's the best Aurora warning app, and is there an NLC equivalent?
Right. NLC, if you go on space weather, this is what I do. There's a picture, but that's 3 days old. I've got friends who go to any live cameras, and they'll go to cameras in Germany and things like that to see what's coming our way. So find, because of the rotation east to west, find cameras, the further east along, the better. Work on the 5-day rule. So if you see the map on the space weather and it sticks out, and you can reckon so about 70 degrees a day, just calculate it out and you can look, oh, right, that was the 21st, it's the 23rd today, right, that'd be 140 degrees round. That's the way I do it. But there are few people with live cameras around. The Shetland webcam I sometimes use, but because the Shetlands is so light at this time of year, it's very, very difficult. But for Aurora, it's brilliant. Again, depending on weather. Aurora warnings, again, these, I use space weather again. I use that speed graph. I see a coronal hole moving in. I say, right, that's, and I normally reckon 500 to 600. I calculate about 3 days. Also, space weather will say, here's a coronal hole. We expect it to impact in that sort of time. And then just watch the speed. And when the speed starts to rise, and then you're on. You know it's on. Because you only get, as a coronal hole comes in, it's more a scatter effect. So you don't get its full effect until it's pointing direct at you. So what you'll see is a gentle rise. So you know it's on. Again, watch it positive or negative. If I've seen on a normal day where it's just doing 350 and then it's gone suddenly negative and stayed negative, we've had terrific aurora. And basically because it breaks into the Earth's magnetic field and it's away. So watch that positive negative bit at the top of the graph, and all that's on space weather. There are several other bits and pieces that look at the sun. I watch it every day and I'll do diary bits and pieces and stuff like that. If I see something, I'll put an aurora alert out. And right now, NLC, I get told, because up here, it doesn't get dark until after it gets dark down south. So, for instance, Pete Muggeridge, he managed to let me know that the Noctilucent clouds were on the 21st, 22nd, before I could see them at all. So I was out there watching for them, but of course it was dark down in London, so he could see them. Anything else? Hello?
Sorry, Sandra, I had my my mute on to avoid interrupting you. Yeah, we've got another 5 questions which have come in.
Right.
So the first one is from Diane, and it's,
Yeah.
do we have any idea as to how much NLCs weigh?
Hardly anything at all. They're minute fragments. It's almost like the rings of Saturn, but even lighter. They're basically held there by the rise in temperature, and it's a really strange one. Weight, I wouldn't like to guess. It's like guessing the weight of a cloud, but they're really, really thin. They're tiny little particles. I mean, if you saw them, you probably wouldn't even see them. Because they're covered in ice, you start to pick them up. But actual weight, I don't think we've even caught any yet. Like I say, it's almost impossible to get there. In fact, one of my plans, should Richard Branson start putting his rockets up, they actually will go at that sort of height. In other words, they'll be around the 80 to 100 kilometers mark, which means they'll be flying through that zone. So it's possible, should he start to get going, that we can get samples and then see what's going on. But very good question, yes.
Next is from James Dawson, and he's
Hi,
asking,
James.
he says, I've never seen NLC higher than Capella from Nottingham, about 53 degrees north. Is this because I'm not looking hard enough, or the sky is not dark enough, or something else?
Right, it would depend on what time you look. Quite often, the displays are quite low. But if you'd have looked on the 21st, 22nd, and you'd had the clear skies, you would have had it much, much higher. And again, it'll depend on whether you've got clear skies or not. The other thing is, watch your 6 to 12 degrees. I've sat and watched it here, and it's been at Capella height. Then as the sun starts to rise, it gets rid of the noctilucent clouds that are low level, but starts to illuminate the ones up overhead. And all of a sudden, all this lot that I couldn't see before suddenly appears. So you've got to have patience. This is the only way I can say it. I use stellarium and check what the height of the sun is, reference to your latitude, and see how far it is below. When it starts moving up to about 6 degrees, it will be lighting much, much further south. So just before it gets rid of everything, you'll see the ones going further south.
Thank you, Sandra. The next question we have is from Gary Poyner. Are we any clearer as to the cause of ice voids in NLC?
So say that again, please.
For the cause of ice voids in NLC.
Ice voids? No. This is a simple answer. It seems to be driven by the wind. The wind will blast bits and pieces all over the place. But until we get up there and really have a good look, that's why we do all this observing. That's what we're trying to find out. We're trying to find out what's going on. It gives us an idea of what the atmosphere is doing at that sort of levels. But really, no, I don't. Sorry about that. We're at the cutting edge, shall we say?
And just a comment from Mike Frost, which is it's a great talk, Sandra.
Oh, thanks, Mike.
We've got a couple more questions, and we've got a third one just come in. The first one is from Gary Hunt, and he asks, some NLCs look like contrails. I don't think that is why they are as they seem to be there for such a long time. Can you say why they form that shape?
Again, no, I don't. My guess is there's a standing wave. Have you ever seen a stream where you get a line and the rock causes a slight bump and you get a standing wave? I think contrail one, and there was a lovely one the other night. In fact, somebody thought it was a contrail. I said, no, that's NLC, because I've had about 6 or 7 reports on that one. But it stayed there for quite some considerable time. If you take a video of it, it may move slightly. But yes, I think what's happening there is you've got a rise in the atmosphere, which makes it either go colder or damper. And the result is that you get what I would call a standing wave. Most NLCs, as you probably know, and people have done videos on this, the whole thing's moving around. It literally is like a sea surface.
Next, we have a question from Peter Loveday. Wonderful talk, thank you. Since studies have focused on Steve, what have we learned about the frequency of appearance and most likely times we might expect to see this phenomenon?
Right. I can actually put you quite accurately on that. Over here, I haven't seen it outside of UT times 2100 to 2230. So anywhere in that time zone. It only lasts for about an hour to an hour and a half, and it's not guaranteed. Having said that, I've had lousy weather and I haven't seen the aurora for quite some time. But when I saw it back then, the aurora wasn't a spectacular one. It was just a tiny little one that we normally get, you know, nice little green arc. And I'd gone up to my water tank, which is about 500 feet above the house, because I thought, hey, that would be a great place to take a picture and I could see down to the coast. And I looked over to Knockhill and there was this column. Wow, that's Steve. So I shot loads and loads of photographs of it. But I can't guarantee you when it's going to come on. To me, it's some sort of balancing. It seems to be something that's trying to balance the upper atmosphere and the movements between magnetic fields. It may be something to do with the belts. But it's a lot to be discovered about that one yet. We're only just digging at it now. How often it appears? On my report levels, I would say we tend to, if I get in a steady stream, about once in every month it'll appear. But again, I'm only going by my reports. If you go over Canada, you see it a lot more frequently. That might be because they're closer to the magnetic pole, etc., etc. But again, I don't know a great deal about it. Nobody does, and we're still sort of studying that one a lot. So, but if I do see it, I will yell. Oh, don't worry about that.
We have another question from James Dawson. Have you ever pushed copper pipe into the ground and run wire between them and with an ammeter in the middle to measure the electrical activity of the atmosphere as a predictor for aurora?
No, I haven't tried that one. I don't know if Ken's tried that or not. Ron Livesey might have. The one thing that most people use was a jam jar magnetometer. I had to go at that one. And once I got it away from all the vibrations of the road traffic, that seemed to work all right. Basically, you just hang a magnet with a mirror on it. But I haven't tried the copper one. And I'll be fascinated if you have it, give it a go, or if anybody's given it a go, give us a yell and I'll pass it on.
And the final question we have is from Peter Carson. He says, "Hi Sandra, enjoyed the talk. You showed the space weather website predicting regions where aurora may be visible in green. Do you have to be under the areas shown in green to see the aurora? Or can you see them if you are outside the green zone, but can see upper mesosphere over the green zones from a distance?"
No, the green zones, you've got to be actually under the green zones by the looks of that one. That's the way that one works. It's if you're under the green zone, if the green zone penetrates down to the top of Scotland, then I'll probably be able to see it. If it penetrates down to the middle of England, you'll be able to see it. They're trying to modify it with all the reports coming in, so that green zone will be where people have reported it and stuff like that. That's the plan. And Aurorasaurus are doing that in combination with various people. They've been in touch with me recently, so we're trying to help them on that one. But it's basically, if you're under the green, if the green bit covers you, you'll see it. If the green bit doesn't cover you and you also see it, then give me a yell and we can tell them, and then they can modify their diagram.
Great. Thank you, Sandra. And thank you once again for a fascinating talk.
I'm glad you all enjoyed it. And thank you very much for all of my reporters. And any reports, please, to sandra-b@hotmail.co.uk, and keep sending them in. And can somebody clear the sky of all the cloud?
And as with this talk and all of the other webinars we've been holding, they're available to watch on the BAA YouTube channel. And that includes, if you missed this morning's talk by Dr. Colin Snodgrass on the latest news in spacecraft exploration of comets and asteroids. Next week, on our usual Wednesday evening webinar at 7 p.m, we have Cook, The Transit of Venus, Aftermath and Legacy by Stuart Coulter. So we hope to see you all there, and wishing everyone a good weekend. Thank you.